it is very good to see so many people here interested in measurement uncertainty evaluation. And Ricardo has given you a short overview of how to use in-house validation data. We will now continue going into the different parts. So how we look upon it in this guide is that we talk about precision and recovery and then other components. And I will not talk about precision, and then Ricardo will talk about recovery, and then Eskil will talk about this issue that is really, really important, and this is how the measurement uncertainty varies with the range. But there is also other components that may be involved. And the idea is, of course, that if we can manage to get all that variation in these two boxes, this is what actually Ivo later already talked about. So I think the real goal is to take in all variations we can see now in the precision. And the uncertainty varies in this way. And Ricardo talked about that you have at a low level, you have a constant standard deviation, and at higher levels, you have a relative standard deviation. And that was why we need to divide the range into 2 or maybe 3 different concentration ranges when we talk about measurement uncertainty. Eskil will later go into this in more detail, because this is actually the most important or difficult task when we do measurement uncertainty evaluation, to find this point where it goes from absolute to relative. And it could be a good estimate to start with what Ricardo said, 2 LOQ, but you need for each method, it of course varies, dependent on the actual precision in that method. I will continue now to look at the high level. And there you can see that the relative standard deviation is constant. So therefore, we will only talk about relative standard deviation. And we could do that with RSD, relative standard deviation, or CV%. So if I have 10% standard deviation, I will have an RSD of 0.1. The symbol that we use in this guide is the S' for indicating that the standard deviation is relative. If we go into the draft guide, when we start the chapter on measurement precision, it says the measurement precision is typically a major uncertainty component that can be easily quantified from experimental data. It can be a major. In many cases, it's about the same as the systematic effect, but it can be easily quantified from experimental data. Yes, but that needs a good thinking and a good planning in order to include all variation in the data. And this I will come to into detail. The first thing is that we need extremely many results to get a good estimate of a standard deviation. If we, for example, if I would have 100 data and I will calculate a standard deviation of 10, that standard deviation, if I would repeat it, could be anywhere between 7 and 13. So it is extremely difficult to calculate a standard deviation. So we need many data. That is the first thing we need to remember. There's an ISO standard that actually has a formula for this, how to calculate the uncertainty, not of the result, but of the obtained standard deviation. If we look to precision, we can have 2 major components. We can have repeatability, and we can have intermediate precision. Intermediate precision is actually if I would be sending results to your laboratory in January, April, September, and December, and I will calculate the variation between these results, then I will get an estimate of this lab's intermediate precision. So it should include all variation between instrument, between personnel, between summer and winter, between maintenance, and so on, in order to really estimate all variation we can see. But let's look at the intermediate precision first. So in this case, if I want to calculate intermediate precision, I need to have a control sample covering the whole analytical process. When we talk about precision here, repeatability or intermediate precision, we always talk about that you follow your method from start to end. So that should include subsampling, it should include all the steps. It should also include, if you, for example, in your method always make free measurements and take a mean value of that, the repeatability and in the intermediate precision in this case is not for each single result, is for the mean values. So if we would have a control sample covering the whole analytical process, could be, for example, cadmium in soil, or it could be, for example, pesticides in a food item, which is subsampled, digested or extracted, and examined exactly the same way as your routine samples. Of course, we need to have it in high concentration, so we will be in that concentration range, and we need to have it from a long time. So actually, validation data is not enough. A month is absolutely not enough to get a good estimate of intermediate precision. I would say you need a year. So what you do is you can get a preliminary estimate of the precision after your validation data, but you have to update that after a longer time. Then you have to review the data for outliers, and there is actually many ways to remove outliers, but there is a very simple, and it works very good, that you just take away 4 standard deviations. That is also a recommendation I used a lot. And from this we can calculate the intermediate relative precision, SI prim. Then we also have the repeatability, the S small r prim. And I think there was a question if I could use routine samples. You could, you should absolutely do that. Because if you can take duplicates of your routine samples and then for a long time period, so this is actually an X chart, should be an R chart here where we look at the difference. I'm sorry for this mistake. You can use routine samples, but you have to look for them in the higher concentration range. And then you use the test results from duplicates, also over a longer time period. And you review the data for clear outliers, as we talked about, and then you can pool the data, the standard deviation, to get your repeatability standard deviation. And this will, of course, include inhomogeneity of samples. So, for example, if I would have analyzed phosphorus in wastewater, I would probably have a control sample with a clean solution of phosphorus. That would not include any variation due to particles in the sample. But if I then combine that uncertainty from the control sample with this repeatability, I think Ricardo actually showed how you could do this combination. Then I will actually incorporate in my precision estimate also the inhomogeneity of the samples. So for me, duplicates over a long time period is one really gold mine for the experimental data. So we can use experimental data, but we really have to use it properly. You could also naturally just measure several samples 10 times under repeatability conditions. And why I say several times is that we say we need a lot of data in order to get a reliable estimate of the standard deviation. I would probably say that the first example that I showed here is better to use, because then you will include different control test samples, different matrices, because you could have a matrix variation, which you also need to include in your precision estimate. And if you then have obtained a repeatability in your method, in your lab, and you use a standard method, you could actually combine that, because in most standard methods, there is an indication of the repeatability you should have. And then you can compare that repeatability with your repeatability in order that you actually fulfill the criteria for that method. So now I briefly explained how you could do this in the higher concentration range with relative standard deviation. You can apply exactly the same approach in the lower range with test samples and control samples in the lower range and do exactly the same calculations. So you come up with two estimates, one absolute and one relative, which also Ricardo mentioned several times. So to summarize, in order to get a good estimate of the precision, you need a long time. I would say at least 1 year. You would need many data to get a reliable estimate of the standard deviation. You will also need to incorporate subsampling in your laboratory. If you are interested not in the uncertainty of the laboratory sample, but also of, for example, the lorry that goes out from the factory, you also need to include sampling, and you can include that in your precision estimate. So you actually are able to include most of the different components in your estimate. Just a final remark is that now I come up with an estimate of the intermediate precision. But sometimes I don't use that in my control. I use wider control limits in my control chart. This you have to bear in mind when you do the uncertainty calculation. If you use control charge with this estimate of intermediate precision that we have here, then you can use them in the measurement uncertainty. But if you, for example, use wider control limits in your control chart, then you need to use that standard deviation in your measurement uncertainty calculation, because you allow a higher variation. And this is very important for the measurement uncertainty calculation for the precision. I will stop there and thank you very much.